everyone, I'm Catherine Denalsa, and our topic for today is maximum coverage location problem. Maximal, Maximal covering location problem, or the MCLP, is one of the most used covering problem in the context of location theory. So, so my topic here is about the location. Um, you can use the MCLP to covering problems within sa location or the networking ng mga problems. So we have this collection, the sets and the input parameters. So we have the sets, the i's and the j's and the n sub I. So i's here is the index and the set of demand nodes, and j's here is the index and the set of potential location for the facilities. N sub I is the set of potential facilities location that can cover the node I within the time or distance S. D sub I and J is the distance between the node I and the potential location for the facility J. So we have this illustration. We have 25 demand nodes. Our I's here. Muna siya. We have the nodes, mga nodes na na-cover and wala na-cover. So, this muna sila ang wala napili. So, we have the J's here's potential facility location, kaning box. And the NI here, the N sub I here is the potential facility location that can cover daw sa node I within sa ato ang I within sa ato ang S. So, our DG sub I J are kanang between siya sa ato ang node I and the potential location for facility G. So we have the input parameters. The P, the number of facilities to be located. S, the maximum allowed time or distance to respond to a request. W sub I, the value that represents the demand associated to node I. So finally, we have decision variables x sub I and y sub j. X sub j and y sub I are considered as binaries. So we have this x sub j. One if a facility daw is located at node G. So 0 if wala siya, wala. So our J sub I here is to represent the coverage of node I, who 1 if node I is covered, otherwise 0. So we have this illustration. So kani sila is kaning y sub j mo ni sila tong mga na-covered, mo ni sila ato wala na-cover. Mani silang mga 0, 0, 0. Kani sila nasa sulod is mga sila ato ang 1. So, we have the mathematical model of the MCLP, or the integer linear programming formulation of MCLP. So we have an objective function to maximize here. We're trying to maximize the demand at I, or the W sub I, multiplied here the Y sub I by a decision variable. If we look at this decision variable, so we have this Y sub I is equal to 1 if 1 is covered by at least one facility and 0 otherwise. So we have this new decision variable here, which is the Y sub I in the objective function. This is subject to a set of constraints. The first one is the is that a demand here can cover only if there is at least one facility in its area, and that can cover it, and then that's all for all the demand nodes. And this one is quite important na magbutang ta og limit on a number of facilities. So another constraint here is we have the summation over all that's G's, right? All facilities, uh, it should be less than or equal to P, could be or could be equal to P. And that kind of depends on what you want, but P, remember, here is the budget that determines how facilities we open. And then we have the decision variables, the x sub j and the x sub y, consider as a binary. Uh, we have the regular integer x sub I, and 1 sub I is in 0 or 1. So we have our example here, our illustration. So we have the demand node I and the facilities, and this is our table. So our decision variable here is the j is equal to um, a, b, and c. So our facilities here, the J's here is the ABC, our potential facility location or our selected location. This is our one variable, and another decision variable is the I here. The I's here is 1, 2, 3, up to 13. So our I's here, our node here is 1 to 13. So this is our facilities and our demand. This is our mga demand. Kani sila. And these are selected potential facility location, the A, B, C. And then we have the formulation of our problem. So our decision variable are the j is equal to a, b, c, and the I is 1 to 13, and are considered as a binary. So here, remember our objective. Our objective is to maximize the demand is covered. So we're gonna have here the maximize the y sub 1 plus y sub 2 plus y sub 3 up to y sub 13. These are objective here, and the subjective to our constraint. See there, for each node of demand node, we're going to try out the constraint. The first one is going to be the XA. XA is greater than 1. XA is greater than 1. As you can see this table, we have the XA, we have the na-covered niya na demand is isa, the A, the XA here. So we have the greater than 1, and next 0. 0 is greater than y2. I mean y2. Y. This is our y. Next 0. Wala siya na-cover na node. And our 3 here is naa sa ato ang si y3 na siya ay na-cover na isa sa XA. XA is greater than y3. And X4 here is na siya na-cover. So X4 is greater than y1. This is y, I mean y and x. And sa 5 is naa sa 6. Sa 7 is 0 is greater than XA, the XA and the XB. We have the XA plus XB is greater than Y8, and sa ato 9 is isa si YB, I mean XB, and sa 10 is wala, sa 11 is naa si XC, sa 12 si XC, sa 13 is wala. Other constraint we have to put together is the XA plus XB plus XC is less than or equal to P. And then we have the integer constraint, the XA, XB, XC is an element of the 0 to 1, and then all the y, we're going to put the y sub 1 up to y sub 13 is an element of 0 and 1. We have the final formulation of this problem. So we can see here the objective function. There are 13 variables. Note that if these demand nodes will covered or not. Subject to, and remember we had something for the first one, the XA is greater than or equal, the X1 is greater than or equal to Y1. And now important to note that C flex does not have the variables on the right hand side, so we have to bring those variables to the left hand side. And for the second, we remember that we had the 0 should be greater than or equal to y, and now we brought y on the left hand side, and it is minus, and so on. Then we have the that constraint that says the number of facility here should be limited to P. Here we're putting P is equal to 1, and then we have the binary, the X sub A, X sub B, X sub C, and Y sub 1 up to Y sub 13. So this these are a model that can be transformed. This is our final formulation of our first example. Our second example, here we have this given illustration. So this and we have this table. They are covered demand and the I's, and we have the J's here are facility, the A, B, C, D, E, and our covered node I. And this table This example can be transformed into our objective function. The maximize P, we have the covered the mga demand, which is the 100 ZA plus 250 ZV plus 200 ZC and 125 ZD and 150 ZE are total covered demands. So our objective, our subject to, our constraint here are as you can see, our table, the covered node, are ang na-cover is ang XA, XB, and XC is greater than the ZA. And so on. We have the located P sites are XA plus XB plus XC plus 6XD plus XE is equal to P, the located P sites, and all variables are 0 to 1 are integrality. So we have the subject 2. We have this linkage constraint. As you can see, our example. Example 1, same ragapon sila. Tanaw mo ang table kung hindi naka-cover ba or wala. And we have the located P sites, the XA plus XB plus XC plus XD plus XE is equal to P. Muna siya itong located P sites, and the integrality nato is when all variables are 0 and 1. So that's all.